Okay. Good afternoon, everyone. Okay. Good afternoon, everyone. Okay. Good afternoon, everyone. All of you, please type in your name. Shriram, Omkar, Gaurav Sastri, Advait, Shreya, and Tridev. Merry Christmas to all of you. Merry Christmas, Devdas. Any plan for the eve today? You're going somewhere? Shreyash. Okay, can we start? Tell me. No plans. Devdas. Okay, Neha. Fine. Sugosh, Ashutosh, Merry Christmas, Kushi. Yes. See, from now onwards, whatever chapter you have in organic chemistry, that is mostly it is memory based because reactions you have to memorize. Okay. Another thing, there are little bit of mechanism. There are mechanism. Those mechanism, if you understand, it is fine. But at the end of the day, eventually you have to memorize the reactions only. That this particular reactions in this reagent will get this product. Okay, and you can simply by read out the reaction, you cannot memorize, you have to practice. Okay, like I always says, uh, organic chemistry for JE point of view, you have to do at least twice, at least 2 times you have to finish organic chemistry from hydrocarbon onwards, like whatever chapter we have after this hydrocarbon, alkyl halide, aryl halide, aldehyde, ketone, carboxylic acid, amines, all these chapters, what all reactions we have into this. To memorize those reactions, at least twice you have to solve before J mains. Okay, next 2020 January. Okay, so that particular thing you keep in mind, and it is not very straightforward that you put some logic and formula and you get the answer like we have done in physical chemistry, right? So there are exceptions also. There are you know a little bit concepts also. All those things you have to keep in mind. So with questions only you will understand. Okay, how and when what product we get. Okay, so hydrocarbon, you see, as the name suggests, in this particular chapter we'll discuss about the compound which are made up of hydrogen and carbon mainly. Okay, there are other compounds also, but main constituents of one of any compounds, organic compounds, is hydrogen and carbon only. Okay, so these are the compounds which are made up of hydrogen and carbon. Right? If you write down CH4, it is a hydrocarbon. C2H6, it is a hydrocarbon. But obviously, there are many derivatives of hydrocarbon also present, right? So organic chemistry, yeah, Ananya, it is still four. Yeah. So organic chemistry is mainly deals with hydrocarbon and its derivative. Correct. So if you see the classification of hydrocarbon, this is classified into mainly two categories. Mainly two categories. The first one is open chain hydrocarbon. I'll write down here only open chain. And the second one is closed chain. Closed chain are nothing but cyclic compound, ring-like structure. Open chain is the straight chain compound, we also call it as acyclic. Acyclic is open chain, cyclic is closed chain, right? This open chain classified again into two categories, and that is saturated and unsaturated. Unsaturated, okay? Saturated compounds are nothing but alkane. Unsaturated are again two types that you already know, alkene and alkyne. Alkene and alkyne, okay? General formula of alkane we already know, CnH2n plus 2. This is CnH2n, and this one is CnH2n minus 2, right? One more term that you probably see in the question, that is homologue and homologous series, okay? So for example, if I write down the various member of alkane family, we'll start with methane, ethane, sorry, propane, butane, and so on, right? So all these methane, ethane, propane, butane belongs to alkane family. So what we say, they are of same homologous series, okay? If you see the molecular formula of methane, I have written there CH4, and ethane it is C2H6. So if you see, the difference of these two is difference of CH2 molecule, right? If you take ethane C2H6 and propane, that is C3H8. In this also, difference, if you see, difference of CH2 molecule. So all these methane, ethane, propane, butane, pentane, hexane, and so on, methane, ethane, propane, butane, pentane, hexane, and so on, they all belongs to the same family, alkane family, and we call it as they belongs to same homologous series. Okay, so this is nothing but a homologous series. This is also a homologous series, and this is also a homologous series, right? And the compounds belongs to same homologous series and having difference of CH2 molecule are called homologue. Okay, so these are methane and ethane are homologue of each other. Ethane and propane are homologue of each other. Ethane and methane are homologue of each other, right? Butane and propane are homologue of each other. So all those molecular compounds belongs to the same homologous series, and the difference in the molecular formula in those compounds is, if it is CH2 molecule, then they are said to be the homologue of each other, right? So two terms I have given you, homologous series and the second one is homologue. So homologues are like methane and ethane. And like this, if you can write down the example, many examples you can write down. So homologue is a term defined for a pair of compounds in which the difference of in the molecular formula is CH2. Okay. In all these organic compounds, or like chapters, hydrocarbon and the coming chapters, the whole chapter is classified is basically into four different segments, you can say. One is you will see a little bit of introduction, then we'll see the preparation method of one particular compound, and then we'll see the properties. In properties we have two different points, chemical and physical properties, and the last one is uses. Usages are not that much important for a competition point of view, but for any compounds, little bit of information you should have. No, methane and propane are not homologous of each other. Successive carbon atom, yes, correct. The difference should be CH2. Okay, so in all these chapters, the chapters are divided into these four segments: introduction, preparation, properties, uses. Order can be anything, but the content will be this only, right? So now coming back to this chapter, hydrocarbon, and the first thing we are discussing here is alkane. Okay, so write down the heading here, that is alkane. Okay, so first of all, in alkane, right, all these information you have, but I'll just write down so that it will be there in your notes. Okay, you can also write it down. Some general information. General formula is CnH2n plus 2. I have already written this. What is the value of dBe or DOU? Any one of you, can you answer this? Yeah, correct. Formula is correct, Advait. So obviously, the general formula is this. This number of carbon atom and hydrogen atom you have, and you can substitute this n2n plus 2 into the formula, you'll get the answer. Okay, and answer you'll get is 0. Okay, formula is correct. Now the point is you can calculate this. It's not 2. Okay, first of all, the formula of degree of unsaturation is C plus 1 minus H plus X minus N divided by 2. This is the formula we have. Now you see, the number of carbon atom is N, so N plus 1. Number of hydrogen atom is 2N plus 2, so 2 into N plus 1. X and N value is 0. So obviously when you solve this, you'll get it 0. Correct? So this is one thing where the formula you can calculate. And this informs you that how many double bond, triple bond, or ring is possible for a given compound, right? And since it is a saturated hydrocarbon, there is no double bond present into this. So that's why its degree of unsaturation is 0. Okay. Alkanes, you can also say, sir, why not this one? This is also cycloalkane, right? Cyclohexane. For this, the degree of unsaturation should be 1 because there is one ring, right? So point is, no, DOU is, yeah, it's correct. Yeah, correct, Trideb. It's right. That's what I'm telling you. You can also directly say there is no double bond or triple bond present or ring present. That's why DOU is 0, right? So when I say alkane, the definition of alkane is what? It is the open chain saturated hydrocarbon. That's why DOU is 0. In this, we do not consider the cyclic compounds. Okay, so you must keep this in mind. Alkene means what? It is an open chain saturated hydrocarbon. This is the definition of alkane. Hydrocarbon. That's why when I say alkane, in alkane we do not consider this kind of molecule, cyclohexane, cyclobutane and all, right? So open chain saturated hydrocarbon alkane, that's why DBE is 0. If you have closed chain saturated hydrocarbon, which is nothing but this saturated hydrocarbon, then it is known as closed chain saturated hydrocarbons are cycloalkane. It's not alkane, it is cycloalkane. Like we have cyclohexane, cyclopropane, cyclobutane, etc. All these are cycloalkane, not alkane. Right? Next, you write down physical properties. Physical properties. First one, and all these things you have to memorize. From C1 to C4 carbon, C1 to C4 compounds, the compounds are colorless, odorless gas. Do you understand what is this C1 to C4? Means methane, ethane, propane, butane. Or in all those compounds where the number of carbon atom belongs to 1 to 4 maximum. Okay, like methane, ethane, propane, butane. All these molecules are colorless, odorless gas. From C5 to C17, 17 carbon. It is colorless, odorless, liquid. If the number of carbon atom if the number of carbon atom is more than or equal to 18, then the compound is exist in the form of Vex-like solid at room temperature. At room temperature. In all these, we have one exception. In organic chemistry, you'll get many exceptions. And what is that exception? The exception is C5, pentane. It exists in gaseous form at room temperature. Because of this structure, neopentane. This one I'm talking about. This one is in gaseous form at room temperature because of the branching. Okay, but this is an exception. You can keep this in mind. Color is not required, Shreya. It is very. There are many compounds. Okay, so color of solid hydrocarbon. See, we are not talking about. See, actually, when I say this C1 to C4, we are talking about the naturally occurring compounds. Okay, color. You can, you can put any color onto that. That is a different thing. Okay, but we are talking about the naturally occurring compound. It's not like when some compounds you see with different color, the color that you can put in according to your choice. Okay, that's a different thing. Okay, you can paint any substance with any color, but that doesn't mean that the color of that compound is that particular color. Okay, all these are for naturally occurring compounds. So no general color is defined for them. Okay, now in this, one of the important property on which the question that they ask is boiling point. Boiling point is inversely proportional to molar mass. As the mass increases, molar mass, the boiling point decreases. Okay, so boiling point of CH4 is more than to that of C2H6 and C3H8. As molecular mass increases, okay. Now another thing is boiling point also decreases with branching in alkane. Branching in alkane. Yeah, it's right, Sriram. It's correct. So branching in alkane means what? Suppose you have pentane, like I have taken one exception of pentane. So when you write down normal pentane, it will be C, 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 and C. Normal pentane. Yeah, we'll go faster, Sean. Just give me a few minutes. And then when you write down this, and then it is this one. So boiling point is maximum for normal, then this one, and then this one. As branching increases, boiling point decreases. So you see the boiling point of this is minimum in all these four, all these three. That's why at room temperature also it exists in gaseous form. That's why it is an exception. Next one, write down properties quickly. Alkanes, these are non-polar compounds. Why it is non-polar? Why these are non-polars? Because whatever compound you write, all carbon atom are sp3 hybridized. So there is no electronegativity difference. That's why there is no charge separation into this. Polarity is because of electronegativity difference and charge, if it is there. Okay, so charge accumulation is possible when we have electronegativity difference. If there is no electronegativity difference, no charge accumulation, and compounds will be non-polar. Right? One last property you write down: as branching increases. Yeah, that's what I am writing down, Shreya. Just a second. As branching increases, surface area surface area decreases. More surface area, more will be the boiling point. More surface area, more will be the boiling point. Okay, and that's why, see, actually when branching increases, surface area decreases because of the van der Waals forces. Okay, but all those things are not required, right? Molecules, the branched molecule like this one, its surface area is lesser than this and then this. Okay, because of branching, the molecules, the atoms are close to, comparatively closer to each other, and that's why the surface area is less. This is because of the better, more van der Waals forces over here, attraction forces. Okay, so these are the few physical properties of alkane we have. Now the important thing here in all these chapter is the preparation method. Preparation method of a compound, and then the chemical properties is also important. So chemical properties we'll discuss later on. Physical we have discussed now. Chemical properties nothing but there also we have chemical reactions. Okay, so in all the chapters we have mainly preparation, where we have reactions, and properties, chemical properties, where again we have reactions. Okay, so these two things are the most important thing in organic chemistry in any chapter. Okay, so preparation method of alkane, preparation of alkane, you write down the heading. Okay, now the first method of preparation, the first method of preparation we have by alkene and alkyne. By alkene and alkyne. In this, the first way, by catalytic hydrogenation. Hydrogenation. Okay. So for this, the catalyst that we use here, catalytic hydrogenation we have, and catalyst that we use for this purpose is nickel, or palladium also we can use, platinum also we can use. All these catalysts we can use. All these things you have to memorize. I'll write down the reaction. Okay. Oh, Shreya is asking melting point. See, melting point is actually also has the same order as boiling point of alkane. The melting point and boiling point has same order, but there is no definite, order of melting point we have for alkane. That's why we are not discussing. Okay, so there is a large variation, but usually we say what as boiling point increases, melting point also increases, or as molecular mass increases, melting point also increases. But again, there are a little bit of variation we have in melting point. That's why we are not discussing it over here. And they also won't ask this question in the exam. But if they ask, you can write down that melting point also follows the same order as boiling point. Okay, but there is no any regular trend. Okay, that is the one thing. Okay, so the catalyst we use here is nickel, platinum, and palladium. Now, suppose the reaction I am writing down is I am taking suppose ethene, which is CH2 double bond CH2. And if this is allowed to react with H2O, hydrogenation means what? Hydrogenation means addition of or reaction with hydrogen in presence of any of these catalysts, nickel, palladium, platinum, around 200 degrees Celsius, around 200 degrees Celsius, these hydrogen atom will attach at one of these, both of these double bonded carbon atom. It's not Rancy, it's Rani nickel, Raney, I think. It's Rani nickel. It's nothing but, see, Rani nickel is nothing but it is a small, the size is very small of that nickel. For reaction purpose, the size of the reactant molecule, even the catalyst, should be smaller so that there will be proper interaction. Okay, so Rani nickel is, we actually take very small size of those things. So you can write down Rani nickel also Raney, not Cy. Okay, and all these um, catalyst, palladium or platinum. So both these hydrogen atom attach on this carbon atom and will get CH3 as the product. Okay, for this reaction it is exothermic in nature. Del H is less than 0. Exothermic. Okay, the catalysts that we use here are metal catalyst. All these are metal. So these metals, I'll just write down here. These are metal catalyst, and they have very high adsorbing properties. Adsorbing properties. You know what is adsorption? Adsorption. What is adsorption? Adsorbing properties, TIES, and hence they provide very high surface area, very high surface area for the reaction to proceed. Okay, understood. It's very high adsorption properties and all. So this thing we have. Now if you take ethyne, okay, alkyne we are taking, suppose CH triple bond CH plus we require 2 moles of H2. Same catalyst, nickel, platinum, palladium, and all, right? Product we get here, CS3, CS3. Okay, both two hydrogen atom attached over here, two hydrogen atom attached over here. Yeah, if the molecule accumulates at the outer surface only, it is not going into the bulk of the molecule, whatever you have, right? So that is adsorption. Okay, absorption is when the molecule goes into the bulk of it. Okay, now in this, like I said, H2 attach onto the carbon atom, but it is not as simple as it is looking over here, right? So here is what in catalytic hydrogenation, syn addition of hydrogen takes place. Okay, syn addition means what? You have done stereochemistry in the school. Stereochemistry, have you finished? Note down this point first. In catalytic hydrogenation, syn addition, of hydrogen takes place. Okay, you haven't done stereochemistry. Okay, that's what that should be done before only. Anyways, you see, what do you understand by syn addition? Suppose we have alkene C double bond C like this. Okay, when hydrogen attach onto this, when you do, I'm not writing down the catalyst and all here. Suppose H2 is there. So what happens in the transition phase? This double bond is about to break, and one of this hydrogen will come over here, and other one comes over here. So in the transition phase, what happens? The C single bond C will be as it is, and the two hydrogen atom joins like this. One hydrogen here and one hydrogen here, because we have bond between this hydrogen atom, we have a double bond between the carbon atom. So what happens? This double bond, pi bond, is about to break, and hydrogen atom is about to attach. Fine, this is the transition phase. Okay, finally what happens? This hydrogen or this pi bond breaks completely, and the carbon atom takes one hydrogen atom like this, and hence the product will get. Okay, now what do you mean by this syn addition? That's the question, right? If you see, this carbon atom is what? sp2 hybridized, and this carbon atom is what? Hybridization. What is the hybridization? sp2. So both carbon atom are sp2 hybridized. It means it is a planar molecule. Correct? It is a planar molecule. When planar molecule is there, then one possibility is what? That one hydrogen will come from the top and other one is come from the bottom. This is one possibility. Another possibility is what? Both hydrogen comes from the same direction, either from the top or from the bottom. Right? So when the hydrogen atom comes from the same direction, either from the top or from the bottom, it is said to be syn addition. When they are coming from the opposite side, one is from the top and other one is from the bottom, then that is anti-addition, right? So in this case, you must remember catalytic hydrogenation, syn addition of hydrogen takes place. It means here you see both hydrogen is coming from the same direction. Okay, this is the transition state we have, and we call it as cyclic transition cyclic transition state, because it forms a cyclic compound here, like you see. Is it clear? Did you understand Syn addition? Okay. Now, few examples you see, like if I give you these questions, here we have double bond. When you heat this with hydrogen, or I'll take this one, suppose. It is D2 in presence of nickel. What is D? D is deuterium. Okay, it is the isotope of hydrogen. Okay, so whenever you see this D, H, it has to, it will behave in the same manner as hydrogen behaves. Okay, so what you can consider this D as a hydrogen only, and you can write down the reaction. But you have to write down D, not H. Okay, so the product here will get what? Either the 2D atom will join from the up or top, from the top or from the bottom, right? So one possibility is there, that the 2D will come from the, will come out of the plane, like this, D and D. And another possibility is what? The 2D will come from the bottom of the plane, so dash. Okay, both possibility we have. And these two molecules are exactly same, identical. Understood? One note you write down here. Write down this note. In hydrogenation of alkene, if we use only nickel as metal catalyst, if we use only nickel as metal catalyst, then the reaction is known as, if only nickel we use, then the reaction is known as Sabatier-Sendrance reaction. If we use only nickel, for example, you see CS3CH double bond CH2 with H2 nickel, then the product will be CH3. This reaction is Sabatier-Sendrance reaction. Next point you write down, due to steric hindrance. Steric hindrance, you know what is steric hindrance? You know what is steric hindrance? Due to steric hindrance in alkene, the alkyne is more reactive towards catalytic hydrogenation. Yeah, obviously, Tridev. You see, sp2 hybridized carbon is converting into sp3. So that will change because the pi bond is breaking. Okay, pi bond is breaking. I'll explain this steric hindrance just a second. Okay, so we can write the rate of hydrogenation is inversely proportional to the steric crowding around pi bond. Okay, so for example, you see, if I ask you the order of rate of hydrogenation, the first molecule is CH2 double bond CH2. The second one is CH2 double bond CH3. The third one is CH3CH double bond CH3. Okay. Now you see the steric crowding is what? Suppose we have carbon-carbon double bond, and on this double bonded carbon atom, only hydrogen is present. Or suppose the another one, if also I take CH3 H H H, this one. Steric hindrance means what? Because of the size of the atom or molecule, there will be little bit of repulsion between them. Size, it's just like you have small space, and in suppose on like in the school, the bench where you sit, right? There, maximum two people can sit comfortably, right? But what happens if I ask three or four students to sit on the same bench? Then what happens? Everyone will push each other, right? That is nothing but the hindrance or steric hindrance. Did you understand? If in the less space, if you want to fit more items or more people into the small bench, then obviously everyone will push each other. So that is nothing but the hindrance because of less available space or more size of the people, right? So that is what steric hindrance means. Okay, now what is the meaning of this here? What is the use of this steric hindrance here? Here you see we have hydrogen and hydrogen. Since the size of hydrogen atom is very small, so we do not consider the steric hindrance here between these two hydrogen atoms. Correct? But when you compare the steric hindrance of CS3 and H here, it is obviously more than the steric hindrance hydrogen and hydrogen here. Because the size of the methyl uh, molecule is obviously more than to that of hydrogen. Correct? So these two will have more steric hindrance than this one. So if I compare the rate of hydrogenation over here in these two molecules, because of the less steric hindrance here, the rate of hydrogen of this one is more than to that of this. Fine. Clear? Did you understand steric hindrance? Because this term you will see very often in organic chemistry. Steric hindrance. It affects a lot of property of the molecule or the reactions. Fine. Now, if I ask you the rate of hydrogenation, order of rate of hydrogenation of this molecule, what will be the order if it is first, second, and third? Where we have the maximum rate of hydrogenation? Correct. First we'll have maximum, then we have second only one CS3, and then we have third two CS3 group. Right? Now this molecule you see, this molecule I'll try to draw the structure of this. We have C double bond C, one CS3 I can write this side, hydrogen may be this side, CS3 here, and then hydrogen here. Another possibility is what? Both CS3 group are on the opposite side, like this. What is this and this? Are they same? These structures are same, yes or no? Tell me. Are they same? Tell me. Okay, now I lost the connection actually. Huh. So yeah, they are cis and trans, right? Yeah, okay, fine. Huh. Okay. So this one is cis form, right? This is, see, the molecular formula is same. It is cis, and this one is trans. Two CS3 group are on the opposite side, and here the two CS3 group are on the same side. Okay, this is actually there in stereoisomerism, which I will discuss. Okay, but little bit of idea you can have when the same molecule, actually we have to understand the priority first, then we can do this. But those things in detail I will discuss in stereoisomerism. Here you see two CS3 group are on the opposite side trans and same side cis. But if you see the name of both the molecule, it is what? It is but2-ene only, right? So the point is the name of the two compounds are same. So if I ask you draw the structure of 2-butene or but2-ene, which one you will draw, this one or this one? That's the confusion, right? So to clear this, they have used this term cis and trans, they have introduced this term cis and trans to clear the structure of the molecule. So if I ask you draw cis 2-butene, you can draw this one. Trans 2-butene, you can draw this one. Okay, now here why I've discussed it here, because here you see both CS3 group are on the same side, so comparatively they have more repulsion here because the distance between the two CS3 molecule is less comparatively. Here the distance is more comparatively. Okay, so because of less distance here, the steric hindrance is comparatively more over here. That's why the rate of hydrogenation of cis form is less than to that of trans form. Is it clear? Understood this? Okay. Now you see this first reaction we have seen the preparation of alkane from alkene and alkyne. The second one you write down, second method, from alkyl halide. From alkyl halide. What is alkyl halide? You know already. RX, right? In alkane, when one hydrogen atom is substituted with halogen group. Okay. So you see there are various reaction, different reaction we have for the preparation of alkane from alkyl halide. So I'll just write down here in one simple page, one page only, and you also write down the same way. When you use LiAlH4 or NaBH4, first you write down, I'll explain this. Then we have Na with dry ether. R1 Zn, and then we have R1 CuLi. See this LiAlH4 and NaBH4. You will see this reactant again very often in organic chemistry. These are reducing agent, both. Reducing agent. And this is the preparation of alkane from a reduction method. The name of LiAlH4 is lithium aluminium hydride. Lithium aluminium hydride. The name of NaBH4 is sodium borohydride. Sodium borohydride. Correct? These two are reducing agent. It provides hydrogen to this molecule. It has nature to provide hydrogen to this molecule. Okay. So in this, what happens? This X halogen group gets substituted from hydrogen and will get alkane as RH. So whatever alkyl group you have here, yeah, sodium borohydride. Whatever alkyl group you have here, that will accept one hydrogen from this agent, LiLH4 and all, right? Na and dry ether, this one is very important, Na ether, and we get here R R plus NaX. This method we call it as Wurtz reaction. WURTZ, Wurtz reaction, is used for the preparation of alkane. See, I am writing down here general reaction, but when you take this Wurtz reaction, we'll take two molecules of alkyl halide. Two molecules of alkyl halide. Means we'll take 2RX reacts with Na. I'll just write down this later on. Okay. R1ZN. This also gives you R1 plus ZNX. This reaction we call it as Franklin reaction. Franklin reaction. When you use this R2CuLi, the product we get here is RR1 plus CuX plus LiX. Okay, and this we call it as COREY, Corey House synthesis. Corey House synthesis. Okay, so these three reactions, the three last reaction that I have written, these are actually coupling reaction. Okay, why coupling reaction? Because you see, this here we use two molecules of this, so this R and R gets coupled. Here this R and R dash joins together, R and R1 joins together. That's why these are coupling reaction. Okay. Grignard reagent we'll discuss later on. Tridev, you let it be. RMGX, that is. Okay. RMGX. This reagent, we call it as Gilman's reagent. Not important, but you write down. No need to memorize this. Just you write down. Gilman's reagent. R1CuLi. Okay. So all these name reactions are important. You have to memorize. This one is very, very important. Wurtz reaction is used for the preparation of alkane. Franklin preparation of alkane. House synthesis preparation of alkane. Okay. Now another thing is what? From all these three methods, can we prepare methane or the alkane which has only one carbon atom? R1 is any alkyl group. You see, Shreya, what happens? We have written here R, right? R is the alkyl group and R1 is also an alkyl group. But these two are different alkyl groups. Suppose one is methyl, so other one is ethyl. One is propyl, so other one is butyl. Like that. Okay, it's just different from this one. That's the point. So we cannot prepare methane from Wurtz, Franklin, and House synthesis because since these are coupling reaction, you see R and R. So at least two carbon atom must be there. We cannot have any compound which has only one carbon atom present. Okay, so these three reactions you write down into this note you write down. Write down these coupling reaction. These coupling reaction cannot form alkane with one carbon atom. Cannot form alkane with one carbon atom. Important. This point is important. Okay. Next, we'll discuss little bit Wurtz reaction in detail that you see. So you write down the heading Wurtz reaction. Write down. This is the preparation method of symmetrical alkane. Is the you see the previous slide here, this one. Here we have the symmetry, right? Here we have symmetry, but since this R and R1 is different, R and R1 is different, so we don't have symmetry over here, right? That's why what we say, Wurtz reaction is useful for the preparation of symmetrical alkane. Understood this? This is the preparation method of symmetrical alkane. It follows free radical mechanism. Okay. Have you studied free radical mechanism? Free radical mechanism, have you studied? Correct. So this particular reaction, this question also they ask that Wood's reaction follows what mechanism? So free radical mechanism. Now you see mechanism we'll discuss quickly here. See the metal that we are using, Na, this metal has free electron. So that free electron it can release, and this is the properties of the metal. Metal we use in the reaction so that it can provide free electrons for the reaction. Okay, so this you write down here, this is the metal. Purpose is to provide free electrons. Okay, free electrons. So next is what the alkyl halide we have, Rx, and we take two molecules. Must you write down here? For Wood's reaction, I have told you already, we take two molecules of alkyl halide, Rx. The alkyl halide that you have here, this electron, the free electron, will take this halogen atom, and we have here two electrons, two bond pair of electrons. One electron is taken up by this halogen atom, and other one is taken up by this alkyl group. So we'll get R dash plus X with one pair of electron and negative charge on it. This is nothing but the free radical. One dot means what? Free radical. Okay. So, and this is true for both the molecules. This happens with both the molecules. Means one alkyl free radical we get from one molecule, another one also gives one molecule, right? So what happens then? This free radical is highly reactive in nature. So this two alkyl free radical combines together and form RR, that is the alkyl group, and Na plus, which is here, takes this X minus and forms NaX. Right? This is how the reaction proceeds in Wood's reaction. Understood? Mechanism is not that important. If you know the product here, you don't need to write down this, because you have multiple choice question, so you have to choose one of the option. So you should know what product we are getting, how the product is forming, right? Now you see the alkyl halide we have CH3Cl. Example I am giving you, CH3Cl allowed to react with Na in dry ether, and two molecules of this we are taking. So what is the product we get here? Can you tell me? Yes, the product will be ethane, which is CH3 CH3 plus NaCl. Major product is this. Okay. We also write down this reaction in this manner also. In the book you must have seen. They have written like this: CH3Cl plus Na plus ClCH3, and they'll write down ether over here. And this is the coupling we have, right? Two molecules of Na also we take, 2Na. So we'll get here CH3, CH3. This alkyl group joins, plus we'll get two molecules of NaCl. Okay. Some limitations we have for Wood's reaction, you write down just 2 points we have in this. First point you write down: I don't have any book now. Why? What happened, Ashutosh? Any book you see, OP Tandon and all, it will be given like this. They have written. Okay. Any book you can see. So limitations are what? Methane cannot be obtained. I have already told you. Methane can't be obtained from this method since it has only one carbon. And one important limitation we have here: fails with this reaction is not possible, or it fails with tertiary alkyl halide. What is tertiary alkyl halide? It is suitable only for symmetrical alkane. Done. Next one you see the reaction which is Franklin reaction. In this reaction, write down, in this reaction, alkyl halide is heated with zinc in inert solvent. So you see again, one alkyl halide is Rx Zn XR dash. When you heat with zinc, then the product will get is RR dash and ZnX. It is actually the same kind of reaction like Wurj only. But the difference here is what? We are getting two different alkyl halide here, right? So we are getting what? Unsymmetrical alkane. Unsymmetrical alkane. Okay, this is, see, in organic chemistry, it's not like only two product will get into this. Okay, I'll give you tertiary. Just give me a second. Tertiary alkyl I'll give you. See, it's not like only one compound will get here. We'll get little bit of this also. I'll write down here R dash R dash symmetrical alkane also. We'll get little bit of R R also here, right? But the major amount will be this one, unsymmetrical one. Okay, so mind this. If they ask you how many total product we'll get, then 1, 2, 3 will be the answer. If they ask you what is the product we get here, then the answer will be this. If they say only product, it means major product. If they say total number of product, then major, minor, all you have to count. Right? So in this question, in this reaction, if they ask you what is the total product we get, then the product will be symmetrical, unsymmetrical, all product, whether it is major or minor. Correct? Tertiary alkyl halide is this trident. Carbon with which the halogen group is attached, that carbon atom must attached with three different carbon atoms. This is tertiary alkyl halide. No, Z and X2 we don't ask, we don't consider, because this is the preparation of alkane. So we consider only alkane, whether it is symmetrical or unsymmetrical. Next one, you see the another reaction we have. Cody House synthesis. Write down in this reaction, in this reaction, alkyl halide is treated with in this reaction, alkyl halide is treated with lithium dialkyl cuprate. Lithium dialkyl cuprate, following up following up the reaction with following up the reaction with alkyl halide
the reaction with alkyl halide again to form an alkane. To form an alkane. Alkane. Okay. Here you make one change I missed here. This is R2. The same alkyl group with R2 here. This one is fine. Now you will understand this. How do we get this here? Okay. So you see this reaction. First of all, suppose the alkyl halide we take is CS3Br, and this is first reacts with Li. Dialkyl cuprate is this LiR2Cu. Two alkyl groups, so dialkyl cuprate. Okay, lithium dialkyl cuprate. It reacts with 2Li in presence of dry ether, and we get here CH3Li plus LiBr. This CH3Li, 2 moles of it, allowed to react with CuI, and it forms LiCH3 whole twice Cu plus lithium iodide. This is dialkyl cuprate. Lithium dialkyl or dimethyl, we can say. No, Franklin reaction mechanism is not required. Wherever it is required, I'll give you. Okay, mechanism for all reactions are not important. So all those things which is required, I'll give you. Don't worry with that. And eventually, if you know the product, you can do the questions easily. It is not exactly same, more or less same. Okay, but that is not a mechanism is not required. So LiCH3 whole twice Cu plus Lia. This is dimethyl cuprate. So these two reactions are the preparation method of this particular reagent. That is Gilman's reagent. Dimethyl lithium dimethyl cuprate. Now when this is allowed to react with the another alkyl halide, I am taking C2H5Br here. Any one you can take. CS3Br here. Here I have taken the different one, C2H5Br plus LiCH3 whole twice Cu. This gives this alkyl group, and this alkyl group joins. So we'll get C2H5 CH3 plus LiBr, lithium bromide. This reaction follows the last one. This is the major reaction of Corey-House synthesis. These two are not major reactions. The reaction of Corey-House synthesis is this. These two reactions I have given you for the preparation of Gilman's reagent, which is nothing but this one. Okay. So if they ask you to write down the reaction of Corey-House synthesis, write down this one. Okay. This reaction actually follows SN2 mechanism. What is SN2 mechanism? I will discuss that. Just you write down now SN2. So this one you see, this is unsymmetrical alkane. Odd number of carbon atom, unsymmetrical alkane. One condition we have here, that this alkyl halide that we are taking here, this one, this must not be tertiary halide. Tertiary halide. If it is tertiary halide, then in this case, elimination reaction takes place. So this also I will discuss in mechanism. Okay, reaction mechanism. Then you can connect all these. Understood? So these are the few conditions. That's why this thing is a little bit difficult, because there are many things you have to keep in mind, and it's not like only 10-15 reactions you have. One chapter has 100 200 reactions. Okay, so that's why the organic is a bit difficult. Once you are doing this, once you are studying, if you are studying, you will feel okay, it is easy, we'll get like this will get the product. But all the reactions you have to keep in mind, that is a bit difficult part. Okay, next preparation method you write down, that is from Grignard reagent. When you have semester end examination of 11th class, so Feb will be off, right? Complete holiday. Okay, fine. See, what is Grignard reagent? Grignard reagent is alkyl magnesium halide. The formula of this is RMgX, alkyl magnesium halide. And in this RMgX, the charge you must keep in mind because it is important. The alkyl group has positive charge R plus, and MgX will have minus charge. R plus, MgX minus. Oh wait, I'll do it. Just a second. This is negative and this is positive. R minus, MgX plus. Okay, this you must keep in mind. Now, In this, what happens? The alkyl group and magnesium bond breaks. Whenever the reaction involves Grignard reagent, because magnesium is a metal and here we have carbon. So CMG bond, if you see, carbon and magnesium bond, this bond is quite polar. This is because of high electronegativity of carbon. CMG bond is quite polar. That's why this bond breaks and the reaction proceeds. Okay, so these are the few information you should have. This reagent you will get in organic chemistry very often. So you must remember all these things. Now in this you write down Grignard reagent undergo Grignard reagent undergo decomposition reactions decomposition reactions with water with water, ammonia, alcohol or amines having active hydrogen atom of amines having active hydrogen atom. What is active hydrogen atom? I'll tell you. First you write down. Having active hydrogen atom to give alkanes corresponding to give alkanes corresponding to the alkyl group of Grignard reagent. Okay, corresponding to an alkyl group of Grignard reagent. Active hydrogen atom means what? All those hydrogen atom attached with attached with highly electronegative elements highly electronegative elements such as oxygen, nitrogen, sulfur, fluorine, or triple bond also. All those hydrogen attached to oxygen, nitrogen, sulfur, fluorine, or triple bond are called active hydrogen. Okay, so now you see the reactions. The preparation method of Grignard reagent is this. This also you must remember. When you have alkyl halide, it reacts with magnesium in presence of ether and we get RMgX. That's just this magnesium introduced in between this R and X. We'll get RMgX. This is the preparation of Grignard reagent. Sometimes this is also required, so you must remember. Now, you see the reaction. Suppose I am taking the Grignard reagent as C2H5 MgBr plus H2O. H plus, acidic medium. Okay, like I said, the alkane forms here corresponding to the alkyl group of Grignard reagent. So the alkyl group, the alkyl group of Grignard reagent is nothing but this C2H5, and this will form alkane when it takes H plus. So R minus, obviously here we have minus, and MgBr we have plus. So this H plus will taken up by this C2H5 and forms C2H6, H5 and H plus. Here Mg plus we have will take OH minus from this water molecule, and we get what? MgOH Br will be as it is. So this is what the alkane we get. Lithium and sodium, I have given you the mechanism of sodium. We are not taking two molecules of this here, right? And magnesium, if it releases electron, it will release two electron, Mg plus to second group element, right? So here the form is, first of all, we are not taking two molecules of this. Formation of R is difficult here. And second thing is what? This requires one electron only in the outermost shell to complete their octet. But this will give two electrons because Mg plus is not stable that much. Mg plus is not that stable. So whenever it loses electron, it will lose two electron. And it requires only one electron. So that's why the reaction in that way is not possible. Is it clear, Tridev? Yes or no? Clear? Tell me any doubt? Can we proceed further? Okay. So this is the reaction with water. Like I said, water with water, ammonia, alcohol, anything. So suppose I'll take the example of alcohol now. Now with this only, if it reacts with alcohol, I am taking HOC2H5. Okay, so what happens here? This H plus is taken up by this C2H5. We'll get C2H5H plus MgBr will be as it is. What is left? OC2H5, right? So OC2H5 will attach with this. If you take ammonia, ammonia is NH3. So I'll write down like this, HNH2. So this H will taken up again by this alkyl group, C2H5H plus MgBr will be as it is with NH2 attached with this magnesium. If you have any alkyne HC triple bond CCH3, with this the product will be again C2H5H plus Mg C triple bond CH3, C triple bond C, single bond CH3 and Br. One last one you write down. If you have acid like C double bond OCH3, again this hydrogen is taken up by this C2H5. So C2H5H plus MgBr, and here we have OOC CH3. Is it clear? So wherever you see when the hydrogen atom is attached with oxygen, nitrogen, triple bond, the hydrogen is taken up by this alkyl group of Grignard reagent and alkane forms. This is the preparation method of alkane from Grignard reagent. Next, can we move on? Next, write down Clemenson reduction. See, last product. See, in all these reaction, what happens, you see, in all this reaction, whatever is left after hydrogen, since this hydrogen is taken up by this C2H5, this hydrogen, and this hydrogen is taken up by the C2H5. And that's why we get C2H5H, C2H5H, H and H. And whatever left, here what is left? OC2H5. So this OC2H5 is attached with Mg here. Similarly, what is left here? NH2 attached with Mg. You see here NH2. What is left here? C triple bond CCH3 attached with Mg. What is left here? CS3CO. OO CCS3 attached with Mg. Must take care of one thing. This magnesium attached with the atom here, with which, atom here from which the hydrogen has been eliminated. So hydrogen is eliminated from oxygen. So Mg is attached with OC2H5, not CH5, C2H5O. Hydrogen is eliminated from nitrogen. So Mg attached with nitrogen. Similarly here with carbon, here with this oxygen. Next one is Clemenson reduction. Write down in this. It involves reduction of carbonyl groups it involves the reduction of carbonyl group of aldehyde and ketone. This is also important, Clemenson reduction. It involves the reduction of carbonyl groups of aldehyde and ketone to methylene group to methylene to methylene group. In bracket you write down methylene group is this. Group is CH2. Carbonyl group of aldehyde and ketone is this. Carbonyl group is C double bond O. So in this reaction, carbonyl group converts into methylene group. It means C double bond O simply converts into CH2. Okay. The reagent we use here, reagent is important, ZnHg with concentrated HCl. This is the reagent of Clemenson reduction. Must remember this. ZnHg with concentrated HCl. So if you see here, if the reaction is this C6H5 C double bond O CH3, this when it is allowed to react with ZnHg with concentrated HCl, then this C double bond O converted into CH2 simply, everything will be same. C6H5 will be as it is. Instead of C double bond O, write down CH2 and then CH3 will be as it is. Understood? Mechanism, if you see, suppose I am taking this R, C double bond O and R. So the product, if this is allowed to react with this, will be R CH2R. Correct? Now you see the mechanism how it goes. H plus. This H plus comes from this acid, conc HCl. Now this H plus will, this lone pair will take this H plus and R C double bond O H positive charge on it and R will get. Further, what happens here, since this oxygen is positively charged, electron deficient, so this will drag the bond pair of pi electron here. So it forms R COH R with positive charge on this carbon atom. Right? Now this Zn that you have, this Zn can easily give two electrons, right? So this will give two electrons and forms Zn plus 2 electrons. This 2 electron is taken up by this carbon atom, positively charged carbon atom. RCOH with 2 electron here, R and 1 negative charge. Again from the acid we'll get 2H plus, which attached with the carbon and the OH group. One H plus will come over here and one H plus will attach on the carbon since it has one negative charge. So we'll take OH2, positive charge here, R and hydrogen will be here, right? Now in this H2O molecules comes out and we get R, CR, H, positive charge on it, plus H2O, right? Again, that zinc has two electrons. It gives this electron to this carbon atom and it forms R, C with two electron, R, H, one negative charge, and in the last we'll add H plus into it. The H plus will take this carbon atom and the product we get here is R, CH2, R. This is the answer. So basically this mechanism you don't have to memorize, okay? You have to just keep in mind whenever this reagent we have ZnHg with conc HCl, this one ZnHg with conc HCl, C double bond O you have to replace with CH2. That is it. Is it clear? Tell me if you understood this. Next, write down by decarboxylation by decarboxylation of carboxylic acid. Next method. Decarboxylation of carboxylic acid means removal of CO2 from carboxylic acid. But this decarboxylation takes place in the form of Na2CO3. Okay, so write down into this first. When sodium salt is heated with soda lime, when sodium salt is heated with soda lime, what is the formula of soda lime? What is the formula of soda lime? When sodium salt is heated with soda lime, see, soda lime is NaOH. But in this process, we add some amount of CaO also into this quick lime. So we'll take the mixture of NaOH and CaO. The purpose of addition of this CaO is, see, this CaO is hygroscopic in nature. Hygroscopic in nature, and it keeps NaOH dry. That's why we add CaO into it. Okay. So decarboxylation, when sodium salt is heated with soda lime is NaOH, but in this reaction we'll take the mixture of NaOH and CaO. Reason is this: alkane forms, alkane forms, and CO2 eliminated, and CO2 eliminated alkane forms and CO2 eliminated in the form of carbonate, CO2 eliminated in the form of carbonate. Hence, we call it as decarboxylation. Hence, we call it as decarboxylation. So, sodium salt, okay? Sodium salt of carboxylic acid will be what? Sodium salt is this R C double bond O O N A plus, when it is heated with NaOH, and we have CaO also. So what happens? This Na2CO3 comes out and we get RH. How this Na2CO3 comes out? You see, this Na2CO3 comes out and forms RH. Okay. So one example you write down: C2H5 COONA plus NaOH heated with CaO. So it forms C2H5H plus Na2CO3, right? So basically this hydrogen and this C2H5 joins, Na2CO3 forms. Here you see one important point. Here it is what? The number of carbon atom, here it is what? 3 carbon atom. Okay. And the number of carbon atom we get here into this alkane is 2 only, right? So in this one note you write down: alkane formed by this process alkane forms by this process has always one carbon has always one carbon less than the number of carbon atom less than the number of carbon atom present the number of carbon atom present in the salt present in the salt. Hence, this method is useful. Hence, this method is useful for the preparation of lower alkanes. This method is useful for the preparation of lower alkanes. Is it clear? Any doubt you have till here? Tell me, any doubt? Okay, fine. So we'll take a break. Okay. I'll take my lunch. 15 minutes break we'll take, and then we'll start again at 3:35. Fine. Yeah, we can get correctly there. We can get methane. Clear. We'll start at 3:35. Fine. Till 4. Yeah, it's till 4. Chalo. See you again at 3:35. Yeah, no, sir. Sir, actually, the front, one of the front gate is locked. It's locked inside. I don't have the key. I need to park my car inside. So where can I get the key? Other gate is open, but I think it would be a bit congested. So if I can get this key, that would be better. So you have the key. Okay. So what? Where you need now, sir? Okay, fine. So if possible, then I will collect it from you. You don't only. Otherwise, I'll collect it tomorrow. Okay, today I'll adjust somehow. Fine, fine. Okay, can you start? Okay. So next preparation method you see. Next preparation method is by electrolysis of sodium or potassium salt. By electrolysis of sodium or potassium salt. Okay, write down into this. In this process, in this process, electrolysis of electrolysis of a concentrated aqueous solution of sodium or potassium salt of a saturated monocarboxylic acid monocarboxylic acid yields higher alkane higher alkane at anode. Higher alkane at anode. This reaction follows free radical mechanism. This reaction follows free radical mechanism. Overall reaction, if I write down in one step, the reaction is this: 2R Na plus 2H2O on electrolysis. It gives RR 2CO2 plus 2NaOH plus H2. This is the reaction we have. Okay. Mechanism, you see, the salt we have of saturated monocarboxylic acid, we can take here potassium salt also, CS3COOK also. This gives you CH3COO minus plus Na plus. Two different, one cation, one anion will get. Now this cation and anion will react at cathode and anode. So you see the reaction of anode two molecules of this we are taking. So 2 CH3COO minus at anode oxidation takes place, will get 2 CH3 COO radical plus 2 electrons. How do we get radical? Radical is nothing but only one electron, this single electron this oxygen has. So one electron is given by one ion of this. Since we have two ions, total 2 electron will get out, right? Now this is a free radical, and the free radical has property that it can dissociate to form another radical also. It can also, free radical has this property to eliminate neutral molecule to get new free radical. Okay, so what happens into this CS3COO radical we have, it eliminates CO2 molecule from itself to form methyl radical, which is CH3, right? All this reaction takes place at anode. This CO2 will go out. Now this 2 CH3 radical will combine together, CH3 CH3, and forms ethane, CH3 CH3. So this is what RR we have, CH3 CH3 will get at anode. So at anode will get the what? Will get the alkane. Now the reaction of cathode, you see, at cathode oxide reduction takes place. So Na electron will get consumed. So we have Na plus, right? 2 Na plus. So this 2 Na plus will take this 2 electron and forms Na metal, which further combines with H2O, because we are taking what? We are taking here concentrated aqueous solution, right? So H2O we have there, which forms 2NaOH and H2O liquid, right? This we call it as cold electrolysis. This method is cold electrolysis. The name of this method is KOLBE electrolysis. This is also important. Is it clear? So 2-3 points we have to memorize here. First of all, in cold electrolysis method, hydrogen gas evolves at cathode, alkane forms at anode. It follows free radical mechanism. This is also important. So these 3 points you must remember. One note you write down into this, the last point in this. One note you write down. When mixture of two salts are taken, suppose I am taking this one RCOONA plus R2COONA. When the mixture of two salts are taken, then we get the mixture of hydrocarbons. We'll get the mixture of hydrocarbons. Like we'll get R1 as one of the compound, R2 is one of the compound. This is one important point. Next point, it is used for the preparation of for the preparation of symmetrical alkane. Which is the another method which is used for the preparation of symmetrical alkane? What is the another method which is used for the preparation of symmetrical alkane? Wurtz reaction. Okay, that's we have done already. So can we prepare alkane methane from this? Can we prepare methane from this? No, because again in this two alkyl group is joining, so we cannot prepare methane. So all these things you must keep in mind. Okay, next one. Write down next. Write down alcohol, comma aldehyde, comma ketones, alcohol, aldehyde, ketones, or fatty acids. Fatty acid are nothing but carboxylic acid. Alcohol, aldehyde, ketones, or fatty acids and their derivatives. Fatty acids and their derivatives are reduced to alkane are reduced to alkane by the use of okay, and the derivatives are reduced to alkane by the use of red phosphorus like this, you write it is also an important reagent. Red phosphorus, red P, you write down red phosphorus with Hi. This is also a reducing agent. Okay. In this process, next line, in this process, the number of carbon atom, the number of carbon atom in alkane will be same as will be same as the number of carbon atom, the number of carbon atom present in the reactant molecule. Okay. So very simple, straightforward reaction we have in this. Suppose we have alcohol, like I said, alcohol, aldehyde and all. Alcohol, suppose I have CS3OH, and if this is reduced with the help of Hi, red phosphorus, temperature we use around 150 degrees Celsius. The product alkane will have the same number of carbon atoms. Since we have one carbon here, so here we'll get CH4. Plus I2 also evolve and H2O. This is the reaction we have in this. Another one you see, if I take CS3CHO aldehyde now, first one is alcohol, second one is aldehyde, red phosphorus. Temperature we use again around 150 degrees Celsius. Two carbon we have here, so C2H6 plus H2O plus 2I2. Second one I'm taking ketone, third one CS3COCH3 plus Hi, red phosphorus, again 150 degrees Celsius. We'll get what? Three carbon we have, so C3H8, equal number of carbon atom, plus H2O plus I2. Ketone and then acid. So acid will take fatty acid is carboxylic acid CS3COOH plus Hi, red phosphorus, temperature around 200 degrees Celsius. Again we have two carbon atom here, so C2H6 plus 2H2O plus 3I2. One example for the derivative of this. CS3COCl plus Hi, again red phosphorus, 200 degrees Celsius, two carbon here. So again C2H6 plus H2O plus HCl plus 3I2. This is what the reaction is. Okay. These are the, these are not important or these product. The important thing is the alkane that you are getting. And whatever the number of carbon atom here we have in the reactant molecule, the same number of carbon atom will present in the alkane that we get in this process. Okay. Even this temperature is also not required. Temperature is also not required for all these. And in organic chemistry, balanced reaction is also not important. You don't have to write down the balanced reaction. Like I have written this reaction, all these reactions are balanced. But if you don't know this also, it's fine. You don't need to balance the reaction. The only concern in this organic chemistry we have, is the product. What product we get? What is the major product we get? Okay. So these are the reactions. In all these reactions, red phosphorus and HI we are using, and we get the alkane in this. Okay. So these are the few method we have seen for the preparation of alkanes. Okay. After this, we have already done physical properties. We are left with chemical properties. Okay. So chemical properties, we will not start today because we don't have time. Okay. So we'll finish chemical properties next class, and then we'll start alkene. Right. Second thing is that you will have. I will take one more class this week. Okay. When I let you know. Okay. Maybe Friday or Thursday. I will let you know. So I'll finish this alkene, and then alkyne is very small chapter. There are very few reactions we have into this. See, one more thing, let me tell you, this hydrocarbon chapter is very important because whatever chapter you are going to study in organic chemistry, there will have questions like this they'll ask. I'll just give you one example. Suppose we have some compound here X, some reagent here R1 gives A, then another reagent R2 gives B, then another reagent R3 gives C. And they'll ask you what is A, B, and C, like this. Suppose the chapter is aldehyde only, aldehyde ketone only. So in this, these are the series reactions which is given. So anywhere you will have the application of all these reactions that we have studied in this chapter so far, and all those reactions which we are going to study in this. So alkane, alkene, these reactions will be useful in all the chapters that we are going to study in coming future. Okay, so this particular chapter you do it properly. Maybe there are chances that this particular reaction, suppose it requires some information of alkene. Okay, here it is for aldehyde. Suppose you're doing aldehyde chapter. If you do not know this one, if you know this also, if you know this reagent also, you cannot do this question. So that's the point. That's why in organic chemistry all the chapters are related. Whatever, see, we have done preparation of alkane from alkene, right? There we have seen the reaction of alkene and how they gives alkane. So whatever the preparation method of alkane, here we have in preparation of alkane, here we have with alkene, this particular reaction will become the chemical reactions of alkene. Okay, so like this the same thing will repeat. Okay, so you have to connect this. That's what I said, I always say that you have to do organic chemistry twice, then only you will start connecting things from one chapter to the another chapter. Anyway, so I'll keep on discussing these things in classes, don't worry with that. Okay, so next class we'll start with chemical properties, and then we'll do alkene also. Fine. Okay, so we'll see you soon. Enjoy. Merry Christmas. Any plan you are going somewhere or not? Evening, or you are here only at home?